Welcome to Astronomy. This is a how-to manual about how to solve problems in the Distance to M31 study guide. The purpose of this is to show you how to find the distance to the Andromeda Galaxy, pretty much as it was done historically. This is very important because it's going to be on the next test. To put things in context, remember the section in Coming of Age of the Milky Way on page 169 to 172. There is a section on Cepheid variable stars right here, and about how they were used by Harlow Shapley in order to find distances to globular clusters within a Milky Way. Then later, on that page down here, it talks about an astronomer named Henrietta Leavitt, who in 1912 found the distance to the Small and Large Magellanic Clouds. Then if you read on 170 of Coming of Age of the Milky Way, it will continue this discussion of her and how it connects to Shapley and his globular clusters. And eventually, if you follow along, you will get to a description of what's called the Shapley-Curtis debate, where Shapley and Curtis disagreed on what the spiral nebulae were. And then, eventually, it starts talking about Edwin Hubble and how Edwin Hubble had actually found the distance to Andromeda. That is the important thing that Edwin Hubble did. There are a number of things that Edwin Hubble got credit for, which will be discussed later, such as Hubble's law and such as the distances to further away galaxies, which are dubious, as to say the least, that he was the primary person who did them. Vesto Slipher made all of the measurements of the speeds of the galaxies called redshift, and it's important to give Slipher the credit he's due. Since the time that this book was written, more evidence has shown that Slipher has done more work on the subject, and that Edwin Hubble actually failed to credit some of Slipher's work, which, as we know, is a breach of scientific etiquette. And now to our sheet at hand. At this time, you should have already read over the full worksheet, and you should have attempted to do the problems yourself at least once. If you have not done that yet, I would suggest that you pause this video and then go and print out the worksheet and give it a try. Now, the first part of this sheet is about the work that Henrietta Leavitt did. It's needed in order to understand how to find the distance to M31, but this first part is not about M31. It's about a much closer galaxy called the Small Magellanic Cloud. And here it describes what it is. The Small Magellanic Cloud is a nearby dwarf galaxy that orbits the Milky Way, so we can assume that each object inside the Small Magellanic Cloud is the same distance from Earth as each other. In 1912, astronomer Henrietta Leavitt of the Harvard College Observatory published a relationship between the period and the brightness of a particular kind of bright variable star called Cepheid variables. Her figures show the minimum and maximum brightness as a function of period. Both figures plot the minimum and maximum brightness in an inverse logarithmic scale called magnitudes. Her figure 1 plots the period in days, and her figure 2 plots the logarithm of the same period also in day. There are two curves because one is for the minimum brightness, which has a bigger magnitude but a lower plot, and the other is the maximum brightness, which is a smaller magnitude upper plot. For example, consider the magnitude of a small Magellanic Cloud Cepheid variable star with a pulsation period of 100 days. From her left-hand plot, you would read about 12.4 magnitude at its dimmest and 11.3 magnitude as its brightest. So to see that, we are going to look down here at her left plot. The example was something of about 100 days, so that would be here. And a period is how long the star takes to get bright and then dim and bright again. So one full cycle of brightening and dimming. So there's 100 days. Now this axis here is the period in days. So I'm going to label it right here on my plot. Otherwise I might forget. And then you can see that if you look at the top curve and the next curve down, this means that if you look at the top curve right here is about, you see this is 13th magnitude, 12th magnitude, that's 11th magnitude. So it's about 11.3. And that's where it's the brightest. When it's the dimmest, it is between about 12.4. So it ranges in magnitude from 11.3 at the brightest to 12.4 at the dimmest. So that's how bright these things, they fluctuate back and forth from brighter to dimmer to brighter to dimmer. And remember, it's confusing because the lower the magnitude, the brighter the object, because the system was set up by Hipparchus during the time of the ancient Greeks. Now let's look at Leavitt's right-hand plot. It is the same exact plot on the vertical axis as her left-hand plot. This is again the magnitude in magnitudes. The magnitude as a function of the, well, it's the period, but this is not the period per se, it is a logarithm of the period. So if you look here, we might as well write this log period in days. Often we'll write it this way because you imagine taking the period and dividing it by whatever one day is in the units of period, which is trivial if you're measuring in days. Now, the 100 here corresponds to the 2 here, because what this means is that the actual period is 10 to the whatever this is power. 10 squared is 100. So if I follow this up, you can see I have a point there and a point there on the line. If I then take my ruler and I then look at it at her best fit line rather than the best fit curve over in the other one, you can see that they correspond to the same values. You see, it's about here and about there. Notice it's a slightly different because back when she wrote this, they didn't have computers to make the fits of the curve. So she used what's called a French curve to do so. While here, she used just her eye and a ruler. Notice that it's always best to compare what's considered the best fit curve, because sometimes these points, there's so few of them, maybe there's some scatter. Okay, now where were we on our reading of the problem statement? Now consider another example. A small magnitude Cepheid with a period of 10 days would range in magnitude from about 14.7 to 13.6. You should look at your sheet and make sure that you can reproduce that yourself before you move on. Now back to the context. This was really one of the greatest discoveries in observational astronomy because while the brightness depends on the distance, the period does not. This became one of the better what are called standard candles, whose luminosity could be determined independently of the distance. In other words, a better standard candle is one that exhibits a small scatter around the trend line when observed at a constant distance, so one can predict what the luminosity should be based on something that does not depend on distance. Cepheid variables get their name from the naked eye star Delta Cephei. And if you look at the bottom, we have a little more context. Cepheid variable stars get their name from the naked eye star Delta Cephei, which is thought to be the prototypical example. Polaris, for example, is another Cepheid variable star. And it, Delta Cepheid, has a pulsation period of 5.4 days and a peak visual magnitude of 3.48. However, despite being close by, its distance remained uncertain until quite recently. Now, pause the video and read over the next part of the worksheet, and the next video will explain the magnitude system.